Occult Confessions is brought to you commercial-free through the generous support of our patrons. Visit occultconfessions.com and click on Donate to help keep the history of the occult on the digital airwaves.
There's a lot about our universe that we don't understand. In fact, more of our universe is comprised of kinds of matter and energy we know almost nothing about. Visible matter makes up about 4% of the universe, most of which takes the form of hydrogen and helium. Probably only 0.03% takes the form of the heavy elements that form, you and me. 23% of the universe is dark matter, which surrounds the galaxies in a ring and pervades our bathtubs, bedrooms, and mailboxes. Not those exclusively, but Physicists believe that 1 billion dark matter particles pass through every square meter of space every second, including passing through you and me. Dark matter is invisible, but it can be detected because of how it bends starlight, like a glass lens. A corollary to dark matter comprising much more of the universe is dark energy. 73% of the universe is made up of dark energy, or the energy of the vacuum of space. Dark energy may create an anti-gravity field which is slowly driving the universe apart. Dark energy and dark matter explain why the galaxy, which Vera Rubin observed rotates very quickly, doesn't spin apart as it's rotating. The galaxies must be surrounded by an invisible halo of dark matter and dark energy that keeps all the stars and planets and stuff from spinning off into nothing. Dark matter and dark energy offer an explanation, but that doesn't make them any less mysterious. The cosmic and quantum worlds are full of these mysteries. Many of the answers seem to hide at the origins of our universe, which physicists seem to understand better and better every day. Or at least, they're able to make more and more likely guesses about it. But what they don't understand yet is what there was before our universe, or what exists at the edges of our universe. What would it mean to fall off into nothing? They also don't understand whether our universe is the only universe. It's possible that our universe is in fact part of a vast multiverse, stretching into unknown spaces and times. It's also, of course, possible that our universe is one of uncountable universes occupying the exact same space. Today on Occult Confessions, we dip our toes into the weird, overlapping worlds of the quantum and the cosmic in search of parallel universes. My name is Dr. Rob C. Thompson, the Supreme Hierophant of the Secret Order of Alchemical Actors, and my partner in interstellar travel, intercosmic, interdimensional travel, is our Knight of the Dangling Serpent, Sir Jacob Wheatley.
Good day. I feel honored that you wanted to take me on this interstellar journey with you. There's nothing more intimate that brings two people together like parallel universes.
Right, popping between parallel universes, the whole plot of Rick and Morty.
Wow, it really is.
This is our buddy comedy about popping between universes. This is it right here.
Interesting. Okay.
Jacob sort of creates alternate universes in his as an occupation. He's a game designer in the world. Studying game design.
This is what I do every day now.
Yeah, you're sort of building the Matrix.
I hate to break the news to everyone, but we're already in it. Just so everyone knows. No, I'm joking. But
Jacob's been tinkering with the edges of it. He knows exactly where it starts and where it ends.
So if anyone's lives are a little off lately, it's just me.
Jacob's just had one too many beers that day.
Pretty much, yeah.
Well, what's your drink of choice?
I'm more of a cider guy myself.
Yeah, me too lately. I love those ciders.
They're pretty good. I like a nice strong bow. That's good.
Oh, yeah. Yeah, Magners. Yeah, nothing wrong with
that. Yeah.
Let's pledge it out. Well, what?
No, I was going to say, wow, we better get some ciders for this.
I know, right? Some sponsorship. Now let's pledge it out. We, the members of the Secret Order of the Alchemical Actors, do solemnly commit ourselves to a full and honest telling of the history of the occult as far as we know it. All right, now that we've got our cider in hand and our, I don't know, whatever it is, fictional characters used to pop between universes. I'm showing my stripes here. I'm not enough of a sci-fi nerd to know the names of these things. There's that guy that gets in the phone booth. He goes, is he do interstellar travel?
The Doctor Who's?
The Doctor's. Is multiple.
Right? Yeah, I think that's like a reincarnation thing. Maybe.
And James Bond does it in Moonraker. And, I'm kidding. That doesn't happen. Anyhow,
that was good.
Let's talk about inflationary theory. That's our fun way of getting into inflationary theory. Wow. Oh, crap. Yeah, we're not going to do an order of confessors today, friends. We're recording in advance. That's all. Trying to get through the COVIDs any way we can. We perceive the universe by detecting light traveling across space, which can take millions of years to reach Earth. Throughout history, physicists and astronomers have wondered why the night sky is black. Have you ever wondered that, Jacob? Have you ever thought, why is it that color?
Yeah, all the time. I go outside every night and I look at it and I'm like, why is it like that? So
is there a color that it would be where you'd say, that's all right, that's normal?
Well, I'm colorblind, so I don't really know.
Oh. So... Why is the night sky no color whatsoever?
Yeah, everything's just gray to me.
So why is it gray? That's what. So if you were asking this question, you would ask, why is it gray?
Yeah, pretty much.
It's an interesting question. Maybe you're asking yourself, well, Rob, it's black because, there's nothing and nothing is black. But it's not really nothing. Think about this. If light is continually traveling toward Earth from all corners of the universe, think about that. Like, all the stars in all the universe are continually projecting light toward us. So why isn't the night sky white?
That's a really good question. Why isn't it, Rob?
So,
I'm going to start freaking out if I don't get that answer soon.
So you were happy when it was gray, but now that it's white,
now I'm like, it should be white.
Do you know, Jacob, our good old friend Edgar Allan Poe was one of the first to suggest a solution to this problem.
Really?
He said it was a bunch of crows and ravens hovering in the sky. No, he didn't say that.
Oh, I was like, probably.
It's just a mass of angry avians.
Ooh, that's scary.
Yeah, it could inspire your next video game.
Thank you.
The light from very distant stars, said Poe, still hasn't reached us yet.
Because they're like slowly dying out, but like what we see could be like gone for 1,000 or plus years.
Right, stars don't live forever. Some have lifespans measuring in the billions of years, but the blackness that we see is actually, so Poe wasn't exactly right about this, but he's onto the right thing here. The blackness we see is the background radiation, which is not visible to us. So Poe is kind of right that there's gaps because of this fact that, it's sort of like you have to picture them like light beams that just haven't gotten there yet. They're like these long strings of light hanging in space.
So the night sky just hasn't loaded in yet.
Yeah, yes. The bandwidth. It's a bandwidth issue.
Got it.
So what we're seeing is that background radiation of space in the gaps between the stars. The blackness and background radiation of the night sky are fairly uniform because they were formed from a single fireball exploding out from a very tiny space at the birth of the universe. Poe didn't say that, but physicists have filled in the gaps since then.
I missed that in one of his stories.
Right, yeah, that's the secret ending of the Telltale Heart.
I thought so. The heart explodes.
And it's a fireball and a universe is formed.
Yeah.
Oh, we'll get there. The universe was originally condensed down into the space of a particle. Imagine that. Your boyfriend, your girlfriend, your boyfriend's girlfriend, your dog, your cat, your cat's dog. All of that was in as tiny as a particle. Everything. Particle. An imbalance in the perfect symmetry between matter and antimatter in favor of matter at the instant of creation allowed for the formation of the universe as we know it. So antimatter, matter, they're in this like perfect yin-yang. You got me?
Okay.
And then they're not, actually.
Oh, well, you didn't have to
Sorry,
say
I lied.
that.
I lied already.
I trusted you, and you lied to me so quick.
What I mean to say is, had they been in a perfect yin-yang, nothing would have existed. But for reasons...
It had to go a little off kilter for us and our cats, dogs, and stuff to come forth.
Right, it just was off kilter, yeah. And don't ask anybody why. I'm not just because I'm not a physicist. Don't ask anybody. Nobody can tell you why it was a little off kilter. They can give you guesses.
It just had a bad
They
day.
don't know why.
That's all.
Or a bad existence, or that's just how it was. Anyway,
Yeah.
for some reason there was this imbalance that then spurred the creation of the universe, just because there was a little extra matter in the mix. And this bears out with even like a lot of creation stories, that there was this imbalance that spurred the creation of everything. So physicists sort of jive with a lot of mythology in that way. Now, dark matter is a mysterious force in the universe, but we're not really talking about dark matter here when I say there was an imbalance between matter and antimatter. I'm talking about antimatter, which is not the same as dark matter. I'm sorry. I apologize for this.
Yeah, no. Still a little burned, but that's fine.
Dark matter is a completely separate thing. Antimatter is the opposite of matter. It has the opposite electromagnetical charge of matter. So that's what we're talking about when we say there was an imbalance at the beginning of the universe. Dark matter is not even in the conversation. I mean, I guess it is, but it's sort of on the matter side of things, not on the antimatter side of things. Anyhow, I apologize. I'm sorry. I apologize for all of this. This is insane. I'm sorry.
It's a little heavy, but it's all right.
Yeah, so I hope everyone was working out this morning, because
we're going to be doing some lifting on this episode.
Going to be doing some lifting, yeah.
Yeah.
In the first trillionth of a second, give or take, anti-gravity caused the universe to rapidly expand faster than the speed of light. Anti-gravity is proportional to the size of the universe, such that as the universe expanded, the anti-gravity force grew, much like gravity grows stronger the more mass a planet has. So think about this. This is Einstein, right? If you have a great big star, it has more gravity. Like our sun has more gravity than the Earth, which is why the Earth rotates around the sun. The sun doesn't rotate around the Earth. You got me?
Okay.
So the bigger a body in space is, the more gravitational pull it has.
Yeah. That makes sense.
Or like, if you look at the planets, we have just that one moon. But if you look at like, Saturn or Jupiter, they have like tons of moons.
They pulled for more. Oh, wow.
Because they have more gravity. Yeah.
Earth could do better if it was bigger, but
just got a little more heft to us. Yeah.
Yeah.
Venus, Mars, they're all basically our size. So it's the big planets that have all the moons. So this is the same case with the universe. When a universe gets bigger, it has more anti-gravitational pull.
Okay.
So that's, I guess, driving its expansion in some way. Again, don't ask me to explain how or why. It's just what's doing it. It is the force pulling the universe apart. So if gravity pulls things together, anti-gravity is pulling everything apart.
Wow.
So that's what's pushing the universe out into, nothing, because whatever is on the edge of the universe.
Whatever's there, who knows? Right. We'll find out eventually. We just got to get pushed farther enough.
Yeah, we got to take quite a trip. So what were we saying? So the turbocharged hyperinflation is what we were experiencing at the very beginning, did not last long, and has since slowed down considerably, but it has stretched space-time to such a degree that it appears flat.
Oh, flat?
Yeah, contrary to the paper you submitted to Science, also Nature, but I think it was Nature that published it ultimately, the universe is not, in fact, shaped like George Clooney.
Yeah, I had my own theories, of which I was hoping someone would agree with, but no one did.
So if we could somehow get in some kind of vessel, or, maybe just, like meditate our way out, we could, and pop out of space-time and look back down. I would turn to Jacob, and Jacob would look down at space-time, and he would say...
It's just flat.
Yeah,
that's pretty sad.
Not shaped like George Clooney.
I was wrong. Oh wait, no, I would have a breakdown. Hold up.
Oh no, we better get back into space time.
Let's get back into our George Clooney shaped spacecraft.
Yes, and back into George Clooney shaped space time. So it's flat, just flat as a pancake. So our three-dimensional universe exists in two-dimensional space-time, kind of. It's flat.
It's flat.
It's not exactly true, but yeah, it's interesting. Anyway, in less than a second, the universe reached roughly the size of our solar system. As the initial heat of the bang cooled, nuclei formed for a period of about 3 minutes, and then for the next 380,000 years, atoms manifested from these nuclei. Got me so far? So we're all made up of atoms. Atoms have a little nucleus inside. Remember from your chemistry class or whatever, your science class in the 8th grade.
I never took chemistry.
Oh, did you take anything where they showed you an atom?
Maybe. I really I avoided it somehow.
It's sort, it's like these little rainbow sprinkles in the middle of a ball, and there's these other rainbow sprinkles floating around the outside that are tinier.
Ah, yes.
I guess it was sort of like scoops of ice cream in the middle, and then the rainbow sprinkles are running around the outside.
That's how they had to teach it to me, because I didn't take a class. Significantly behind. But anyways.
So we started out with just the scoops of ice cream, and then the rainbow sprinkles accumulated, and then we started to have atoms. So for 1 billion years, the stars formed, and then for another 6.5 billion years, expansion accelerated, driven by anti-gravity, pushing us further and further apart. And 13.7 billion years passed, and at that point, the universe assumed its current status and temperature. Oh. So our universe is 13.7 billion years old.
Wow. Jeez.
And it is 2.7 degrees. That's the temperature of the universe.
2.7. That's so cold.
Yeah.
Wow.
Yes. It's the temperature of George Clooney, space-time.
George Clooney is 2.7 degrees.
Yes. Yeah. It's not clear how or why inflation started, so it's possible it could happen again, or is happening right now, with new universes of varying sizes forming in space. So it's conceivable, friends, that, remember, there was just a little particle, and then boom. Where was that particle before? Maybe it was in another universe. Maybe our universe formed within another universe. Maybe within our universe, new universes are coming.
Oh, another one is forming as we speak.
It could be shaped like...
Jennifer Lawrence.
Jennifer Lawrence. It's possible. It's possible.
So, my type expands from George Clooney to Jennifer Lawrence. That's how it's...
Weird and wild world of multiverse out there. It's not clear. Okay, so what are we saying? So the light elements up to mass 5 and 8 were created with the birth of the universe. The heavier elements like iron were cooked in the furnace of stars, and the heaviest elements like copper and zinc and gold were blasted out in supernovas. This reflects the increasing rarity of these elements on Earth. So the lightest elements we'd have a lot of, like gas and stuff. And then the heavier ones like gold. Gold. Everybody wants gold because there's not as much of it. Yeah. That stuff in your cell phone, like whatever. Titanium, I don't know.
Gold and
whatever's
titanium.
In there. That thing the Chinese are digging it up somewhere. Anyhow. Black holes. Time for black holes. You ready for this?
Hell yeah. I mean, heck yeah. I don't know.
Well, maybe hell's appropriate when we think about a black hole.
Yeah.
They may be the seeds for new universes. So they may actually be like, giant universe vaginas.
Oh.
Birthing new universes.
Oh, you're saying it comes out of the black hole. I was thinking we had to go into it to...
I'm not really saying anything specific here. Let's get into the details. Carl, I'm just trying to be cute. Carl Schwarzschild discovered the strange properties of dark stars or black holes, which form when large enough stars burn out and collapse under the weight of their own gravity. So how we get a black hole, FYI, is that a star burns out. Because stars are sort of like, giant furnaces, and they have a finite amount of energy. Just like, if you're burning a fire in your house, eventually it'll burn out. That's just like a star. But when the star burns out, it's sort of, if it's big enough, if it has enough mass and weight and stuff, it'll collapse on itself and form this black hole.
Whoa. It's just a huge vacuum.
Yes, essentially, yeah. This gives black holes an incredible mass relative to other cosmic bodies. They're essentially hyper-condensed matter, as Jacob's saying, a vacuum. Sort of like the sun's gravitational pull holds the Earth in rotation around it. A black hole has an even stronger pull, so it wouldn't things do rotate around black holes, but, theoretically it is sort of vacuuming things in.
Uh-oh. That sounds dangerous.
It is, yeah. We don't want to get too close to one if we can avoid it.
Yeah.
It's possible that these densely packed dark stars are more or less the same as the tiny particle that was the origin of the universe. Think about that. So the star explodes, and then it shrinks real tight in this tiny little ball of super condensed matter. Maybe that's the seed from whence the universe grows.
Oh. Huh. Interesting.
Lee Smolin argues that universes are like organisms in that they evolve. Let's suppose that universes sprout from black holes. If that's the case, then the universes that dominate the multiverse will have the most black holes, or children which form duplicates of themselves. The optimal conditions to have more black holes happen to coincide with the optimal conditions for life. Possibly. This is all theoretical. Mm-hmm. So you get what I'm saying? It's sort of like, if you are particularly fertile, you'll have more children. Well, what does it mean for a universe to be fertile? It means that it has more black holes, or the conditions that create black holes.
Yeah.
And it just so happens the conditions that create black holes are the conditions that lead to planets like Earth where life can exist.
Got you. Okay. Yeah, I see.
So universes evolve to have life in them in this way. Schwarzschild described a magic sphere around the dark star, now known as the event horizon, which is the point at which anything crossing the sphere would be pulled instantly in by the black hole's intense gravitational pull, the vacuum, Jacob, you mentioned. According to Einstein's theory of relativity, the incredible mass of the black hole distorts time. So time gets slower around heavier objects. A spaceship passing through a black hole's event horizon would be crushed instantly from the driver's perspective, but would take thousands of years to be destroyed from the view of an outside observer. Isn't that weird?
Whoa. That is really weird.
Time slows down when you get close to these heavy things from the perspective of the outside observer. To escape this terrible fate, the ship would have to travel faster than the speed of light, which is impossible since, as Einstein argued, mass reaches infinity at the speed of light. For the ship to travel fast enough, it would also have to be infinitely heavy.
Which, how is that possible?
Right?
Yeah.
What a beautiful day to take the old space cruiser out for a ride around the rim of a black hole. Is it just me, or is the current a little stronger than usual today here on the rim of this black hole? It's probably just me, because the black hole's gravitational pull should be fairly consistent. Oh no. It's got me. It's crushing me. I'm getting crushed much faster than I could theoretically convey the fact that I'm getting crushed.
Oh, what a beautiful day to watch an old space cruiser go out for a ride around the rim of a black hole from the safety of a version of Earth in which we can easily see black holes in the sky. Oh, would you look at that? Looks like Carl went and got himself caught beyond the event horizon, where he will inevitably crush to death long after my great-grandchildren have died. Crazy Carl! He'll outlive us all.
All right, this brings us back to black holes' other potential role in the multiverse theory beyond their potentiality as universe seeds. Theoretically, it is possible to pass through a black hole if you can harness enough negative matter, which is not the same as antimatter.
That's a different thing?
It's a different thing, because antimatter has mass, and negative matter would not have mass, it would have negative mass.
Okay.
So
I'm just going to roll with it.
Negative matter actually floats up rather than falling down to the Earth's surface because it has negative mass. It also possesses anti-gravity, which would counteract the crushing gravity of the black hole.
Okay.
So
yeah, makes sense. I get it.
Yeah, it's just if it has antimatter and anti-gravity, then fine.
Yeah, that's all right.
Somebody writing those damn Marvel movies is copiously taking notes right now.
You're welcome.
Yeah, right. This is how we restart the Spider-Man series again.
Yeah.
If we could, not that they give a shit about really justifying it. Let's just do it again.
I mean, they have the option to, so.
Right. What if Spider-Man is a duck this time? What if it's a duck in a spider costume? What about that? We'll try that.
Well, there's a spider pig, so yeah.
Why not? Why not? Who needs anti-gravity to explain this? It's just the way it is.
Yeah.
If we could pass through a black hole, a distortion of space-time, we could theoretically travel across the multiverse or to a different era or universe, breaking the known laws of time and space.
Whoa. So not only can we go to a different universe, we could time travel? Is that what you're saying? Because you said
Theoretically.
era. Wow.
Yeah, they are distortions in time and space to the degree that they would allow us to move through time and space in ways that we don't traditionally, which is to say that we move through space, in a linear way, and we move through time in a linear way. Time is always going in one direction, but not in a black hole.
Wow. So the movie Ant-Man was almost right.
I suppose, in its way.
Yeah.
What a beautiful day to take the old space cruiser out on a ride around the rim of a black hole. Is it just me, or is the current a little stronger than usual today here on the rim of this black hole? Oh no, it's got me. Good thing I brought this can of grade A negative space matter from the Negative Matter store, where all purchases are theoretical and the payments are cash only. I guess I won't get crushed today, just whisked off to another random universe on the other side of the galaxy. Hope it's not the crab people universe again. Everything tastes like clams there.
The multiverse. You ready for the multiverse? If that wasn't enough for you.
Oh, I'm so excited for the multiverse.
That's just the prelude to the multiverse. So we sort of have to get all that stuff out of the way. You have to grasp the basics of black holes and stuff. And again, let me tell you all, you don't have to understand why. Because a lot of the physicists don't really understand why any of these things are true. When I'm talking about anti-negative matter and stuff, like, nobody can show you that. No one can draw you a picture of that, It's a theoretical idea. Yeah. So don't worry about that too much. So let's get into the multiverse. It's just like Spider-Man. Like, who cares? We started again. It's a pig now.
Yeah.
As soon as we admit that our universe had a starting point, we open up the possibility that other universes exist with their own starting points. It's possible that universes spontaneously break off from each other at random points in space and time, and our universe just so happened to be lucky enough to expand the way it did. This goes back to my idea of the little seeds and the universes growing within universes.
Is it like roots and stuff?
Yeah. There's these little shoots. They shoot off from each other.
Okay.
The black holes. So if you got all that down, that the black hole could be a seed, then you're with me so far. Physicists imagine the multiverse as a collection of interconnected bubbles of varying sizes and curvature. It's dominated by large universes like ours. Each universe has different physical constants and therefore different laws of physics than ours, though. So we can have really tiny universes that are, like your thumbnail or, I don't know, smaller. And we can have enormous universes. You could be like walking past a universe on your way to the, convenience store.
Whoa.
It could happen. You're going to get some Magners at the liquor store and you pass a universe.
I'll leave them just for them, just in case.
One just, sprung up right there.
Exactly.
But that's dominated, most of the multiverse would be large universes. Our universe is considered to be quite big. Or they're of course guessing because they don't know. But it feels big. It feels pretty big to me.
Yeah, it seems big.
Yeah. I mean, relative to me, it's a pretty big place.
Yeah.
My house is small, but the universe is huge.
It's pretty big. Yeah.
There are 4 fundamental forces in our universe: gravity, electromagnetism, weak nuclear force, which is radioactive decay, and strong nuclear force, which, holds together your atoms. Gravity is the weakest of these, followed by electromagnetism, which is substantially stronger than gravity, but still weaker than the nuclear forces. When our universe formed, the 4 fundamental forces were unified as one, but became separated, with gravity splitting off first, prompting a great shockwave. So all the forces were just one force, the force. And then they became 4 forces. Gravity split off first, was like, I'm going to go do my own thing, you guys. And then the universe was like, oh shit. And there's a boom, shockwave.
Wow.
Yeah. Parallel universes are a quantum expansion on the multiverse, suggesting that a universe can exist in multiple states at the same time. physicists suspect that these forces and their relation to each other may be unique to our universe if there are, in fact, multiple universes. Each universe would then have its own laws. Yeah?
Okay, yeah, no, that makes sense. I think. I'm just gonna say yes.
All right, now this is just like a little aside here. I don't want anyone to get too hung up on these things. String theory says there are many different subatomic particles, but in string theory, they are all actually the same subatomic string vibrating at different frequencies. So everything, the hadrons, the electrons, what am I saying, hadrons? The electrons and protons, and they're all actually the same thing vibrating at different frequencies. That's basically string theory.
So like vibrating at different like frequencies creates like different things, right?
The different kinds of vibration yield what physicists perceive as different subatomic entities.
I guess that could make sense in the terms of like with the Big Bang, how it all was just like one tiny ball and everything just came from it. So technically everything is the same, just different.
It's just a little side thought. Mm-hmm. All right, so now let's get into some approaches to the multiverse. Let's start with the many worlds theory. The many worlds theory begins with the classic cat-in-a-box experiment proposed by Erwin Schrödinger. We've done this one before. We place a cat in a box with a device that is triggered by a subatomic particle kicked off by radioactive decay. According to quantum physics, subatomic particles exist in two places at once until they are observed. We did this in our Soul series, so you can go back in there, and we get into this in more depth on the quantum soul, I think I called it. Mm-hmm. So feel free to go back there. But I'm just going to do a brief summary here. Jacob's taken a class with me on this, so he's heard me do this spiel before.
I have indeed.
So
it's all coming back now.
Once they are observed, the wave function collapses and the electron is either in one place or the other. And so, while the cat is in the box, it is both dead and alive, since the subatomic particle has both triggered the device, killing the cat, and shot off in a different direction. So sometimes people think about Schrödinger's cat like, well, the lid's closed, so I don't know if the cat's dead or alive. But the reason the cat is both dead and alive is because it was a subatomic particle in the experiment that caused the thing to live or die. And a subatomic particle exists in two states at once until somebody observes it. Then it collapses into one.
Yes.
Yes. You gotta listen to that episode. Yeah. Anyhow, we're gonna just carry on here. Okay, so... when we look, quantum superposition collapses down to a single option. This idea was logically absurd. Okay, so I said this like, that's just the way it is, that the cat's both dead and alive, that the particle's in two places, and then we look, and then it's just one place. But, until we look, the cat's living and it's dead all at the same time. This is logically absurd. It's okay.
Yeah, it does sound pretty far-fetched, because wouldn't it just be one or the other?
Right. I mean, in our experience of the world, we don't walk around seeing, children that are both on the sliding board and under the sliding board, or children, or, dogs that are both, eating a bone and not eating a bone. The bone is not both there and in the dog's stomach. Like, things don't exist in two states at once. Mm-hmm. So the same is true of the cat.
Okay.
Logically, it just doesn't make sense. But it does pose a fundamental problem for physicists that they've been wrestling with ever since, because when they do their experiments, they see that subatomic particles can exist in two states at once until they're observed. So what do we do with that? So Hugh Everett III is one of the big heroes of today's podcast. He proposed a radical solution to this problem. The term many worlds theory was coined by his friend and editor, the physicist Bryce DeWitt, when he retitled Everett's idea to publish as a book. He said, the cat is both dead and alive, but in separate universes.
Whoa.
In one universe, the cat is killed, and in another, it is not. We exist in one iteration of a never-ending sequence of universes. This is Hugh Everett III here. Mm-hmm. Interestingly, these universes are all overlapping each other in space, but they exist as separate energy frequencies having decohered from each other.
What does that mean?
It means that every time we're in a situation where the subatomic particle exists in two states, that at that moment the universe splits.
Oh, then it splits into two different universes.
A new one splits off. Yeah, I mean, it's hard to even say two because there would be uncountable numbers of universes.
Yeah.
Because just in having this conversation, Jacob, subatomic particles in our brains have been making all kinds of choices.
Oh, okay.
There's a universe in which we never had this conversation. There's a universe where midway through this conversation, your microphone caught fire. There's a universe in which I am conducting this conversation from Florida and you're in Annapolis. There's a universe in which, you know what I mean?
Wow. Okay.
Yeah.
Huh.
Yep.
Well, I'm sorry to the one that you're in Florida. Just to put that out there.
You apologize to that me.
Yeah, I hope he hears me.
All right, so let me try to explain this in greater depth. Everett asked us, incidentally, my kid's name is Everett, so
wow.
I was doing this research. I didn't name him after Hugh Everett III, but after Katie and I had picked his name, I was conducting this research, and it just so happened to center around Hugh Everett III. Anyway.
That's pretty funny.
He asked us to imagine that we're looking at a big pointer like an arrow pointing to a subatomic particle in superposition. So imagine a great big arrow is pointing at this subatomic particle, and the particle is in two places simultaneously. So if the arrow is trying to keep pointed at the particle, it would appear smeared out, is what he says, because it's sort of vacillated. It's going back and forth. It's going, it's going back and forth and back and forth and back and forth because a particle, the arrow is trying to point to the particle, and the particle is in two places at once. So if we tried to see the arrow, it would look like a blur to us. It would be smeared out.
Okay.
Except, like if you take a picture, right when your hand is moving.
Yeah.
You know what I mean? That's what it would look like. Except, says Everett, we don't. What we see is one arrow in one position showing us where the electron is, because that's how quantum physics works. When we choose to observe a subatomic particle, we never see it, and we can't see it in two places. It's always in one place or the other. But it could just as easily be in the left as in the right position or the right as in the left. It just picks one when we look at it.
So is it I don't know if there's an answer for this, but is it the same particle or is it a different one?
Well, who are we asking?
I guess just either, if anyone has an answer.
It's whether the electron is behaving as a wave or behaving as a particle determines what position it will be in, but it behaves as both a wave and a particle until we look at it. Then the superposition collapses. So Everett's saying that in theory, we should be looking at this, particle doing both things at the same time and looking super weird, but in fact, we just see one particle hanging out, like, hey, what's the big deal? This is the collapse of the wave function. When a particle in superposition is observed, the particle collapses down to one spot. But Everett said, that goes against pretty much everything we know about reality.
Yeah. Yeah, I mean, he's right.
It makes more sense to say that we have become smeared while looking at the smeared arrow, and so it only appears to us that it isn't smeared. In other words, if we imagine an electron bouncing back and forth, it won't and it's not looking, it won't look smeared to us if we're also bouncing back and forth in the exact same way.
Okay, it makes sense.
So because I'm standing still and looking at the arrow and it's moving back and forth, I'm like, oh, that arrow is all wonky. But if I am moving with the arrow in the exact same way, the arrow will appear stationary to me. So Everett says it makes more sense that we suddenly start moving back and forth with the arrow than that us looking at the arrow somehow causes it to stop. Because that's cause and effect doesn't make too much sense there. Everett used the metaphor of an amoeba to describe what's happened to us. We've split into two identical beings, sort of like an amoeba, with all of our physical characteristics and memories preserved in both copies. So when we encounter the quantum particle in superposition, the arrow flipping back and forth, it appears to us as just one arrow because we have split into two. And one of us is looking at the arrow that landed on the left, and one of us is looking at the particle arrow that landed on the right.
Whoa.
Yeah. We're in both places at once.
That's crazy.
We just didn't notice.
Yeah.
So, each observer is mistakenly viewing a deterministic world in which all possibilities happen as an indeterministic world where only one of two possibilities has come to pass because the observer has partial information and can't take a fully objective view, which would have to be from the outside of the unfolding parallel universes looking in. So we'd have to get this, again, me and Jacob getting in our little craft and somehow hovering outside of parallel universes. Because we're in the universe, we didn't notice that we split one off. But if we were at a third perspective, if we got outside of this splitting, we're hovering above, hoping to see George Clooney, we would see the two universes separate from each other.
Wow.
Yeah. But we can't because we're in it.
Yeah, because we're observing it.
Yeah, because we're living it.
Ah, got it.
We don't have the outside view of the thing happening.
Yeah.
Sort of like, it's the difference between watching a train pass and being in the train.
Okay.
You know?
I see.
You get that outside view of the train, because if you're inside a train, it doesn't appear to be moving at all.
Yeah.
Right? Unless you look out the window. If you're just, looking inside the train, it seems like the train's not moving.
Yeah.
But the outside observer sees the train moving. Same situation with the splitting of the universes. You have to get outside to see that it's split. If you're in, you didn't notice.
That's really deep. We got to get out of this train.
Important to Everett's theory is that the universe experiences quantum superposition and splits regardless of whether a human is observing it. All objects, microscopic and macroscopic, exist in superposition, entangling with each other and continually splitting into separate universes. The universe isn't splitting, we're splitting along with the object we've become and entangled with it into separate universes. So it's not even just about this observer, really, says Everett. For this to all logically make sense, all quantum particles have to constantly be splitting off universes all the time. That's why I said they're uncountable.
Hey, Carl, is that a new lamp?
That it is, Biff. It's powered by radioactive decay. No, don't look at it.
Too late!
Never look directly into a lamp that's powered by radioactive decay. Now you've gone and split yourself into two universes. And in this one, I'm being a dick about inviting you into my house with a radioactive lamp and telling you not to look at it, and then busting your balls for it.
Yeah, this universe kind of sucks. What's happening in the other one?
Lamp exploded and killed us both.
Steven Weinberg compared this to listening to a radio. The frequencies for various stations are all out there for us to pick up, but we can only pick up the frequency of one station at a time. The waves of each universe vibrate at different frequencies, and so we cannot tune ourselves to them. Got me?
Oh, okay. Yeah.
So it falls into a different frequency, and we can't hear it anymore. The dark side of the many worlds theory is that no matter what we do, an infinite number of other versions of us are doing the exact opposite or something else entirely. All of our actions are in that sense pointless, since we're always doing everything all the time. No decision truly matters.
Ooh, that's a little sad.
Yeah, that is pretty dark, right? If you're like, should I take this job? Should I, date this guy or girl? Should I...
It doesn't matter.
I don't know. Right? It doesn't matter because in another universe you didn't do it.
Wow.
In another universe, there is no occult confessions. I just make YouTube videos about putting on makeup or something. Yeah, I went another way.
Huh.
And in another universe, I just garden.
I assumed you already garden, but
I do garden, but that's all I do. That's it.
Okay.
In another universe, I'm a fundamentalist Christian.
I don't know about that.
But you have to imagine it, right? That's what's so depressing about it. I mean, you have to imagine these scenarios where you're like, no, I've definitely not made that choice. So, Jacob, the worst things you could imagine, you've done them.
Wow, that's pretty dark.
Yes. Yeah. Yeah, you got married at 19. You have 4 children.
That's so. If I had said yes when I was 19, it would have been a very different life.
Right. You were cured. You had your kids. You're living that life somewhere
Cured
out
at
there.
17.
That's what's dark about it, though. I mean,
Wow.
I guess I'm really trying to get a rise. I don't know what I'm doing to you. I'm making you feel bad, but it's because that's what makes it so dark, because you really the worst of the worst you've done. Like the worst things you could think you could have done to yourself.
Yeah.
You have done them somewhere.
So in a few other universes, I wouldn't get along with myself then. I think
Yes.
in most of them, I wouldn't get along with myself.
Almost none of them, because what makes us who we are is that we've made these choices and that we've rejected the alternative. I mean,
That's
except
crazy.
except for the regrets we might have. You know, I wish I would have done this or that, but yeah.
I was thinking about it like, wow, that would be cool to like meet another one of myself, but I don't think so. So
Maybe a couple of them, like some of them that are very close to us, it might be cool. But the ones that have made, very different choices from us, we might not be so thrilled with.
yeah.
So interestingly, this affected Hugh Everett III's life. He died at 51, which is pretty young. He smoked 3 packs of cigarettes a day.
Oh.
And he ate and drank to excess. He believed in quantum immortality. Follow me here.
Okay. Yes.
Quantum immortality means every occasion of death splits off a version of yourself that survives.
So
Because whatever you did to lead to you dying, you didn't die in another universe.
I don't know if this is too dark to ask, but was that intentional then?
I don't think he was suicidal, but I think that he never really cared about his health because he believed that in alternate universes, he wasn't smoking 3 packs. So why not be the version of him that's enjoying cigarettes and whiskey?
Okay. Huh.
As an atheist, he asked that his ashes be tossed in the trash when he died.
Wow, he really was saying nothing matters.
Essentially because he's out there still. There's still a Hugh Everett III somewhere. His wife kept him in an urn for a while before tossing him in the trash, as he requested.
Well, that's nice that she kept his wishes.
It gets get dark, I'm sorry here. His daughter committed suicide in 1996, and she made the same request in hopes that she might end up in the correct parallel universe to meet her father. Oh, God.
Oh, jeez.
But Mark Oliver Everett became the lead singer for a band that I enjoy called Eels, a great alternative rock band.
Okay.
So isn't that something? The inventor of the many worlds theory, his son is the lead singer for an alternative rock band.
Yeah, I didn't know that.
And I'm not even kidding. They're on my Spotify playlist like ages before I started doing this research. So
yeah, they're a good band.
You've listened to Eels, yeah.
Yeah, they're a good band.
I think they have new music out recently.
Wow.
Critics have noted flaws in the theory of quantum immortality. First, is that it's unfalsifiable because we cannot communicate between universes. Second, this is the many worlds theory in general. Second is that the vagueness, uncertainty, and arbitrariness surrounding the collapse of the wave function has simply been shifted to when and why worlds split off. So, while Everett thought he was solving the logical quandary of Schrodinger's cat, he's really just creating a whole shit ton more quandaries.
Yeah, I was about to say, there's a lot more to go off
logically,
now.
yeah. There's a whole lot more problems now. Challenges persist in resolving the differences between relativity and quantum mechanics, as well as between the subatomic and macroscopic universe.
Mm-hmm.
So for all these reasons, we should not rely on the notion that we are quantumly immortal and that our choices don't matter. We should make choices.
Yeah, I mean, why don't you live the best life,
Yeah, either way, you're this one, but there are no guarantees from a physics standpoint that there are any universes splitting off where you've made any better decisions. So
it's not like if we were to do something, it's not like we would necessarily hop into that one, right?
It's probably not even there logically.
Yeah.
Because Everett said, it's arbitrary that the wave function collapses when we observe it. Mm-hmm. I mean, really what they're saying here, but But now we have to say, well, it's arbitrary when universes split off, and it's arbitrary what causes them to split off.
Yeah.
So it's just like there's still the problem of things just being arbitrary. So we can't rely on this being the solution.
Yeah.
Many worlds theory remains highly, highly speculative. So still make good choices. Don't get married at 19, Jacob. Too late.
I won't. Yeah,
I will not become a fundamentalist Christian. We will continue to do what we think is meaningful.
Yeah, we're doing good.
Speaking of meaningful, so I wanted to get many worlds I find a bit dark and unsettling. So I wanted to do the last portion of today's episode on something that I find more encouraging.
Ooh.
And that's the anthropic principle, or the anthropic principle. This is the idea that the laws of nature are arranged so that life and consciousness are possible. So think about that. That means that space-time was created so that we could exist.
Wow. That's very sweet.
Right?
Thanks, space-time.
Thanks, George Clooney. Thanks, Jennifer
George
Lawrence.
Yeah.
Jennifer Clooney.
Jennifer Clooney. George Lawrence.
All of them. Mm-hmm. There is substantial evidence that the conditions on Earth and in this universe are special. To begin, the moon is exactly the right size. Hear me out. It's about the third the size of Earth and prevents the Earth from wobbling off its axis. So the Earth would orbit, we would wobble. We wouldn't keep a steady axis, but for the rotation of the moon around us. Is there rotation? Revolutions of the moon around us. Mm-hmm. Because of that, we stay steady. If we didn't stay steady, it would cause drastic changes in the climate, which would make it very difficult for us to live the way we do. We'd have to be constantly moving.
Yeah.
And moving like great distances. Jupiter's immense gravity keeps asteroids from constantly pelting us.
Oh. Thanks, Jupiter.
Yeah, right? We've never had cause to reflect on how cool Jupiter is, but it's super cool. The Earth itself is exactly the right size to have the gravitational pull to keep oxygen in its atmosphere, but not so large as to retain the poisonous gases that were emitted when the Earth was born. So if we were a little bit bigger, we'd be holding in all that poison gas. It wouldn't have been able to escape off into space. If we were a little bit smaller, oxygen would float off into space and we would die.
Yeah. Wow. There you have it.
Yeah. So be careful when you're digging.
You might get some gas, you know?
Or you might your oxygen might float off.
Oh, yeah.
But I mean, that's amazing, right?
Yeah, that is pretty cool.
If the solar system were closer to the black hole at the center of the galaxy, the radiation from the black hole would kill off all life on Earth. If it were further away, Earth wouldn't contain the higher elements necessary to create life. Mm-hmm. Hugh Ross compared the likelihood of Earth's formation to a Boeing 747 pulling together as a result of a tornado striking a junkyard.
Wow. Okay.
That's how unlikely it is that our planet should exist. It's as if a tornado hit a junkyard and a plane formed out of it.
That's wild.
That's the anthropic principle.
Huh, okay, so I have heard that in, like, classes before, that they've said, like, I mean, obviously, like, everything is just right, so that way we can live and stuff, but, like, it's pretty neat, you know.
There are two versions of this. There's the weak principle and the strong principle. The weak principle says that there's a form of self-selection. We observe our universe, therefore we must be in a universe that allows for the existence of observers. It's possible to imagine many possible universes with different laws of physics. Our universe has our laws of physics and physical circumstances necessary to create carbon-based observers, namely us. So we see that this universe has the condition to create life because we exist to see it. That's the weak anthropic principle.
Okay.
The strong anthropic principle is much cooler. It says the universe must have these properties which allow life to develop within it at some stage in its history. Let me try and compare these. On the weak principle, it's, there's all these different universes out there, or there could be, and it just so happens that ours randomly had these characteristics. On the strong principle, it says that no matter what, the universe will always create the conditions for life.
Oh, okay.
The participatory anthropic principle is even cooler. It says observers are necessary to bring the universe into being.
Ooh.
So the universe can't exist without us to observe it.
So if we just stop observing it, it's just done.
If we all closed our eyes, yeah, that would be it. Existence would blink out.
Huh. I've been researching a lot of apocalypse myths and stuff lately, and I think that's the coolest.
We all enter sensory deprivation chambers, and that's how the universe ends.
Yeah.
All right, so let me try and explain how these all function. Let's start with delayed choice experiments. I know it's painful, but that goes back to Schrodinger's cat. Again, Soul episode. According to delayed choice experiments, or not accordingly, they demonstrate that the future can influence the past on the quantum level. Suppose an electron is given two paths to travel and has to make a choice a light year away. The electron can go down both paths at once, but doesn't want me to know that because it upsets my sense of the laws of physics, in which a thing can only be one place at one time. So, if I decide to observe a light year later which path it went down, it will choose path 1 or path 2. But if I don't choose to observe, it will choose both paths. So this is coming from billions of light years away, and I'm observing it billions of years later. But it's only going to make the choice, right? It already left. That light particle left, but it'll somehow make that choice a billion years ago based on what I did a billion years later.
So it just knows?
It's time travel, man.
Whoa. Oh, jeez. Wow.
So here's the interesting thing, if it's not interesting already. I'm making my decision to observe, this is basically what I'm saying, long after the electron has decided which path to go down. But when I make my observation, it echoes back through the past, changes what the electron does. Both paths, or one or the other. My future decision, just to summarize here, my future decision influences the past, which is the opposite of how cause and effect work. This technically happens with starlight navigating around cosmic bodies. It can go both ways until I observe it, and it must choose a single path. We need to get that down for a second, let that absorb into your head, and now I'm going to make this even more fun. John Wheeler. John Wheeler says, it makes more sense to say that the observer brings the electron's path into being. It didn't have a path before I looked. Significantly, in my little scenario, no one watched the electron leave. I only watched it arrive a light year away. The observer determines the shape and nature of the universe, is what Wheeler is saying. My consciousness is sufficiently strong to determine the path of an electron, but Wheeler wonders if there are beings more conscious than us who can determine the electron's existence through observation.
Oh.
So God-like beings, I guess, is what we would call them from our, mortal perspective here on Earth. On Earth, our conscious power can change how electrons behave and all this sort of stuff. The superposition that Everett tried to solve.
Yeah.
Wheeler's saying, what if our consciousness has the power to determine what these tiny particles do? And if that's true, we can imagine a more powerful conscious being, a being who's more conscious than us, who can determine whether the electron exists or doesn't exist.
Whoa. That's really cool.
Rising levels of consciousness then bring the full universe into being. So we have sort of like a chain of angels who are more and more conscious.
And just getting more woke.
Right. And as they're perceiving, the universe is existing. If we can shape the path of an electron, they can shape the existence of electron. Then there's someone who can shape the existence of nucleus. Well, I guess we got to electron, so we can move on to, atom, and then a body, and then a planet, and then a star. On and on and on.
Wow.
All the way up to the final observer with a capital F and a capital O, talking about the big man or woman.
The big FO.
The big FO. Making an ultimate observation. The final observer makes an ultimate observation to bring the full universe into being. God. Whoa. God observes the universe into being.
Jeez.
Wow, right?
That's insane.
Barrow and Tipler suggest that this final observer must exist outside of quantum spacetime, or the observer would itself need its own observer to come into being.
Yeah.
Right? Everything needs a cause. So the ultimate cause, the God cause exists outside of space-time. That's right next to us. When we're looking down, looking for George Clooney and just seeing flat, God is like, what
right
are you
there.
guys doing here? Yeah, he's sitting right next to us. Like,
That's
how'd you
so
guys
cool.
get here? What are you doing here?
So is he like they? I don't want to say he because they are they at the end of it looking at like, or are they? So well, okay. So there also is. This one character, speaking of Marvel, that is called the Observer. That's what they do, is to just observe like universes and stuff and like the multiverse, and they just look at it, but they just look at it to record the events and stuff.
Well, that's almost quantum physics. If the observer's act of looking created the universe, then we're in quantum physics.
Wow. Okay.
So to answer your question of where the observer exists, the observer is likely a future observer existing at the singularity when the universe condenses down, or at a point when the universe becomes infinite.
Oh, okay.
Because there are two ideas about what could happen to our universe. Our universe either expands out infinitely, or our universe suddenly condenses back down into a tiny black hole-y particle seed and then explodes again and back and forth like an accordion.
Okay. Wow.
In this theory, consciousness appears destined to become coextensive with the cosmos to observe the whole of creation. So consciousness and the universe are necessary to each other. Without consciousness, there is no universe. Without a universe, there is no place for consciousness to reside. So they're sort of feeding each other. Einstein and Newton both believed in the existence of God. Newton was a theologian as well as a mathematician and scientist. Einstein believed that the Old One, is what he called God, didn't intervene in the affairs of men, but sought to read the mind of God with his theories. So in other words, Einstein said, God stays out of everything that's going on here, you guys, which in a way is what quantum physics is saying here. These, Barrow and Tipler, is that God must be outside of space and time. But Einstein also conceived of himself as reading the mind of God when he tried to understand the physical laws of the universe. Marveling at how the rate of the expansion of the universe could have been 1 part in 100,000th of a million off and collapsed again, Stephen Hawking suggested our knowledge of the Big Bang clearly had religious implications. So that's just a little tour of some of the big minds in physics and their God beliefs.
Oh.
The final anthropic principle. So we did the participatory principle. Now let's do the final anthropic principle. Getting us close to coming on home today.
Cool.
Intelligent. I know, it's been a rough ride. Not rough. It's been a fun ride, right, Jacob?
No,
Mind expanding.
Yeah.
It's better than drugs.
It's so much better than drugs.
Who needs LSD?
Yeah, when you have quantum physics.
Right? The final anthropic principle says this: intelligent information processing must come into existence in the universe, and once it comes into existence, it will never die out. There's a fundamental metaphysical question in the final anthropic principle. What would be the purpose of having conscious observers and information processing in the universe if we were going to die out before we could have any measurable effect on the universe? For Tipler in particular, our destiny as conscious beings is to colonize the universe.
Colonization. Cool.
I mean, do you get what he's saying here?
No, not really. I heard colonize and it just went straight over my head.
So, essentially what Tipler's meditating on is that the universe is constantly expanding. And the dark, unpleasant side of this is that because the universe is constantly expanding, that means everything will continue to get further and further apart from each other, and the energy of the universe will wind down, essentially creating conditions so that nothing can exist. But Tipler, in contrast to this, is saying that there is no reason for conscious observers to come into being if consciousness can't have any impact on the nature of the universe itself.
Oh, okay.
So, this idea that the universe is going to sort of die out doesn't make any sense, because we as conscious beings will in some way influence the universe to prevent it from dying out.
I see. Okay.
Well, conceivably. I mean, that's one version of it, but that our conscious minds, which, as we've seen, make some changes in the universe, that our conscious minds are meant to evolve to a point where they make a change.
Oh, that's cool. We're just at the beginning of this.
See? And that's enough.
Interesting.
We've done enough work for today. I think that is a nice thought to end on.
Wow.
Any comments, Jacob, on that tour? I mean, you've had plenty to say along the way, so I don't want to put any pressure. But
I mean, I've said so much this time.
Because it's just us, just you and me.
I know.
Going through those alternate universes, popping out, talking to God, looking for George Clooney, living our lives.
That's. I like that. That would be like a fun book. Wait, no, that's going to be my game. It's going to be our adventure through. Yeah, so thank you.
It.
I'll get on that.
You're going to have quantum adventures.
Yeah.
My sources today include Michio Kaku's Parallel Worlds, A Journey Through Creation, Higher Dimensions, and the Future of the Cosmos, published by Doubleday in 2005. Peter Burns' The Many Worlds of Hugh Everett III, Multiple Universes, Mutual Assured Destruction, and the Meltdown of a Nuclear Family. John Barrow and Frank Tipler's The Anthropic Cosmological Principle, and Frank Tipler's The Physics of Immortality. Which we certainly explored today.
We did indeed.
Do you know how to bring us on home? I mean, it's a lot of pressure being the only one.
I know. I think I know it.
Go for it.
All right.
By bring us on home, I mean back into space-time.
Okay, all right. I don't know how to do that, so we're kind of stuck here now.
Just use the usual ritual. It'll do the work.
Okay, got it. I hereby and declare closed this meeting of the Secret Order of Alchemical Actors until such a time as we get together and do it again.
Very nice. Our voices today are Luke Kinnaman and Andrew Mims. And here we are. Rob C. Thompson, your Supreme Hierophant, joined by Jacob Wheatley, Knight of the Dangling Serpent. And did you say bye-bye?
Sorry. I was too
you were
busy
in
thinking
another
about
universe.
Space. Yeah. Wait, we can call ourselves the Interstellar Duo now.
We can, yes.
Yeah.
Well, so sign off, Interstellar Duo.
I don't know. Space.
Time.
Ooh.
On our next episode, we will consider celebrity clones and whether we are all, in fact, clones. And is Paul McCartney dead? And is Britney a clone? That's coming up here on Occult Confessions.
Wow.
Yeah, we take a hard turn from quantum physics to pop culture.
Wow, I'm glad I could be here for this.